So, I guess I'll get started with announcements. So the last set of worksheets on chapter 6 through 9 and the last homework are both due on the 2nd. That's, after Thanksgiving. And the presentations and the papers are due on the 4th. And if you look on Brightspace, you'll see they're due at they should be due at the time of the class. So make sure you have your presentation ready before class, and preferably you provided, you need to make sure your topic's been accepted. You do a 2 to 3 page paper on the topic. Let me just. Make that clear. A 5 to 10 minute presentation on the topic. And the presentations will start on the 4th. The schedule is up on Brightspace. So make sure your slides are going to be ready before class. You can do this by submitting them on Brightspace as a PowerPoint. Then I can download them and you can then present them in class, or you can bring them on a USB stick or something like that. You need to submit your slides anyways. So if you submit them as a PowerPoint to Brightspace, you can use that to present. Also, if you have like a PDF of it, that'll also work. You can also use that to present. And then lastly, the exam on chapters 6 through 9 will be on the 2nd. Now we're actually probably going to cover a little more material past chapter 9 because we're starting chapter 9 today. We're going to finish it before we run out of classes for lecture. But chapter 9 is the end of what's going to be on the test. I'll just cover some more material that we'll talk about, but it's not going to be on the test. So we are starting chapter 9. Chapter 9 is on running water and groundwater. So we talked about weathering. Now we're going to talk about what happens after weathering. In many ways, stuff gets moved by water. So let's talk about what happens with water. Water is the most important source of erosion, the movement of weathered particles, and it's a huge factor on what occurs on Earth. So we'll talk about the hydrosphere, which is the distribution of water throughout the Earth. We'll talk about its major reservoirs and describe the different paths that water will take through the hydrologic cycle. We'll describe the nature of drainage basins and river systems and go over 4 different basic drainage patterns. We'll talk about stream flow and the factors that can cause it to change. We'll talk about the ways in which streams erode, transport, and deposit sediment. We'll contrast bedrock and alluvial stream channels. We'll distinguish between the 2 types of alluvial channels. We'll contrast narrow V-shaped valleys, broad valleys with floodplains, and valleys that display incised meanders. We'll discuss the formation of deltas, natural levees, and alluvial fans. We'll distinguish between regional floods and flash floods and describe some common flood control measures. We'll discuss the importance of groundwater and describe its distribution and movement. We'll compare and contrast wells, artesian systems, and springs. We'll list and discuss 3 important environmental problems associated with groundwater. And we'll explain the formation of caverns and the development of karst topography. So the Earth is a system, and there's a cycle of water throughout various states known as the hydrologic cycle. And the distribution of water throughout the world, we talk about where that water is located. The hydrologic cycle describes the circulation of the Earth's water supply. Now, most of the water on Earth is in the oceans. They are huge. There's a lot of water there. So most of the water on Earth is water in the oceans. It's salt water in the oceans. But that water will evaporate, transfer into the atmosphere, where it can condense and precipitate, much of it raining back into the ocean, but some of it precipitating on land. And on land, it can travel as runoff, or it can infiltrate the ground and become groundwater. And the water on the land can evaporate or transpire to return back to the atmosphere. So there's a constant cycle of water leaving surface supplies, going into the atmosphere, and then falling as precipitation. So the processes involved in the water cycle are precipitation, water leaving the atmosphere by falling, evaporation, water entering the atmosphere by evaporating, infiltration, that's the process of water seeping into the ground, runoff, runoff is the process of water moving across the surface of the earth. This is, water rolling across your lawn after a rain, but also streams, rivers, lakes, things like that. And evapotranspiration. Evapotranspiration is what plants do. They take water up from the ground and release it into the atmosphere. And the water balance is the volume of water that passes through each cycle annually, every year. And this cycle is, continuous and is always moving. So there's a constant flow of water evaporating, precipitating, infiltrating, and running off, and re-evaporating, and so on. So there's this water cycle, this constant movement of water from one state to another, which feeds all precipitation and streams and everything else.
Hello there, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the basic functioning of the water cycle and describe what proportion of the world's water is found in rivers. Here's an example of a river. It's flowing through a relatively arid region of the world. Rivers like this are the lifeblood of communities that live in these dry parts of the world, and they're also the most important agent for sculpting the landscape. But river water is actually a very small percentage of the total water in the world. Most of the water in the world is found in the oceans, about 96.5% of all the water. A small additional component is found in saline lakes and saline groundwater. And of all the water in the world, only about 2.5% is fresh water. Now we want to zoom in on that 2.5% and examine it closer up. Of the 2.5% of the world's water that is fresh water, about 68% of that is present in glaciers or ice sheets. Of the part that's not frozen, we see groundwater, and then there's about 1.3% of the total that is surface water and other fresh water. And once again, we want to zoom in on that water, take a look at what it is. And you can see that actually, even though it's not part of glacial ice, there's still snow and ice is a large part of that, around 73%. Around 20% is in lakes. All right, so even though lakes are really prominent on our maps, they're only 20% of 1.3% of 2.5%. Of the part that's not snow and ice and the part that's not lakes, we've got soil moisture, swamp water, the water that's in our atmosphere, the water that's in living organisms, and then the only thing left, the remaining paltry 0.46%, is present in rivers. So rivers are a tiny proportion of a tiny proportion of a tiny proportion of the world's water, yet they are quite important. Rivers are part of the water cycle. The water cycle is driven by heat energy that's provided by the sun, and that sun energy warms up water that evaporates. It evaporates and enters the air. As it is in the air, it can end up settling out again in the form of precipitation. This is either rain or sleet or snow. And as it falls down onto the land, basically that water has three options. Option number one is that it can evaporate again and go back into the clouds. Option number two is it can soak into the soil and go underground, and we call that infiltration. And option number three is it doesn't re-evaporate, it doesn't soak into the ground, and instead it simply runs off over the surface of the earth. And that, of course, would be the water that ends up in rivers. Okay, is this an example of evaporation, infiltration, or runoff? Well, hopefully you identified this as a cave, and you know that caves are underground. Caves are carved by groundwater, and so the water would have had to have infiltrated in order to produce this cave, not run off or re-evaporated. Good job. Thanks very much for your attention. This has been another Smart Figure.
So running water is an important part of our lives, and it's an important part in shaping the landscape. The amount of water that remains on the surface as runoff depends on a variety of factors. How much water there was, the intensity and duration of the rainfall. Very intense short rainfall could put out so much water that it can't infiltrate easily. There's just not enough time for that to happen, so you can get a lot more runoff. Yes? Uh, thousands or millions of years? Long time. Probably thousands of years. Thousands to millions, yeah. I'm not entirely sure. But I mean, those are dissolved away slowly by slightly acidic groundwater. So they're not fast at all. We use deposits like that in those caves to do things like look at ancient climates. Because they, you get a layer each year kind of thing. But long time. Not 100% sure, because my background's not actually in geology. But a long time, yeah. The amount of water that remains on the surface as runoff, it depends on how much rain there is, the intensity and duration, how much water is already in the soil, the nature of the material at the surface. If you pave the surface, you get a lot more runoff than if you have nice water. That's an easy thing. The slope of the land, and the extent and type of vegetation. So when rainfall exceeds the amount of water that can be absorbed by the ground, you get runoff of excess water. And as this water flows over the surface of the ground, it can be particularly erosive in areas without vegetation, like a freshly plowed field or something like that. And generally, runoff doesn't happen over very long distances before it will either soak into the ground or empty into a stream. And a stream is any flow of water with two defined banks. So from a tiny little brook up to the Mississippi, it's all a stream from the geologist point. So any channeled flow of water between two well-defined banks is a stream. So for a geologist, the size of the channel flow doesn't matter. Both the Mississippi and a tiny mountain brook are considered streams. And as a stream flows, other material gets transported with it. And that's called the stream load, which we'll get into later. So when you have running water flowing into a stream, there's an area that feeds into that stream. And that's called a drainage basin. And the drainage basin of two separate streams are separated by a divide. We're actually close to one of the least impressive divides out there. We're close to a divide about what flows into the Mississippi and what flows further east. And what flows into the Great Lakes, basically, and flows further east. But it's basically invisible because this whole area was scraped flat by glaciers. But yes, the separation of drainage basins. So you have a drainage basin, that's the area that flows into a particular stream. And you can build a bunch of drainage basins, connect together to form the drainage basin for like a big thing. So the drainage basin of the Mississippi covers like half the US. And then between drainage basins, you have divides. So when you describe a drainage basin, there's basically three parts. Near the source of the river, at the headwaters, you have a zone of sediment production. This is where streams are picking up material. They're wearing away the material, they're carrying it away from these places. So this is like up in the mountains or wherever the body of water is starting. In the middle, you have a zone of transportation, where in general streams are mostly just carrying along material. This is, the trunk stream, something like this. I mean, there's probably deposition and recollection, but mostly transport. And then lastly, at the end, at the mouth of the river, you have a zone of sediment deposition, where the sediment carried in the stream gets dumped out, often into the ocean. And networks of streams will form various distinctive patterns based off of the landscape they're on top of. And the drainage pattern will vary based on the terrain involved. So some common drainage patterns are dendritic, which means tree-like, rectangular, which is rectangular, radial, and trellis. So a dendritic pattern, this develops on relatively uniform surfaces. There's no particularly weak spots. So you get a sort of random tree-like branching structure. Looks kind of like a tree. If you have a highly jointed bedrock with lots of cracks built into it, the streams will tend to flow along the cracks, and you'll get a rectangular pattern. If you have some sort of isolated cone, like on a volcanic cone or on a dome, you can get a radial pattern where all the streams are traveling outwards from some location. And the trellis pattern develops in areas where you have alternating weak and resistant rock. So the weak areas get worn away and you get these long strips, but the resistant areas only break through in a couple of spots. So you get these long parallel strips connected by sort of a trunk going through a few gaps. Now, if you want to figure out how fast a stream is going to flow, the flow of a stream depends on a few factors. How fast that water travels depends on, well, the first factor is just how steep the slope is. Because the steeper the slope, the more gravity is going to pull the water down, the faster it's going to flow. Also, characteristics of the channel. The shape, size, and roughness of the channel help determine the speed of the water. Basically, if you have a very rough channel, that slows the water down. If you have a very big channel, that helps actually speed the water up because there's less interactions with the edge of the channel, and the shape of the channel could affect how much it slows the water down. And then lastly, the discharge, the volume of water flowing in the stream. And that generally gets bigger as you head downstream as more sources of water feed into the stream. And this is generally expressed as cubic feet per second. So the size of the stream and the discharge kind of, at some level, determine how fast the water has to flow. Because there's so much water needs to make it through, there's only so much space for it to go. So if you have a sudden decrease in size, you can actually have a speed up, but it's a bit complicated. But let's talk about some of the biggest rivers in the US. The biggest river in the US is the Mississippi. It feeds, the basin feeding the Mississippi travels all the way over from the Appalachians, all the way over all towards the Rockies. It's this huge area. And so it's one of the biggest rivers in the world. So here's a video about various rivers in the US and which ones are the biggest.
Hello, I'm Michael Collier. On this field trip, we'll be flying over parts of the Mississippi River to see how the largest river in the United States flows from its source to the sea. 75 million people live and work in the 31 states and 2 Canadian provinces that make up the river's drainage basin. They all need water from the river to live here, and at the same time they all use the river to dispose of household, industrial, and agricultural wastes. On our way downstream, we'll try to understand how the Mississippi grows and flows, how it creates landscapes in its floodplain, and how people have come to live and work alongside it. The Mississippi's official source, or headwaters, is Lake Itasca, 1,475 feet above sea level in northern Minnesota. Let's travel downstream, 2,340 miles to its mouth where the river empties into the Gulf of Mexico. This is more than just one river. Tributaries add water from the whole basin, more than 1 million square miles stretching from the Rocky Mountains to the Appalachians. That's 41% of the contiguous United States. Only the Congo and Amazon river basins are larger. One major tributary, the Missouri River, is actually twice as long as the upper Mississippi above their confluence. Another, the Ohio River, delivers a lot more water to the main stem channel than the upper Mississippi. Go figure. But rather than debating about which branch is the longest or carries the most water, we can think instead about an entire basin with multiple tributaries, the Missouri, Ohio, the upper Mississippi, all coming together to form the main trunk of the single mighty river. The Mississippi River is dynamic. It's always changing. Did you know that its current flows faster along the outside of a bend than on the inside? Because of this difference, water erodes the outside of a bend to form features called cut banks. Water on the inside moves slower and tends to drop its load of sand to form point bars. In this way, the river continuously creates loops called meanders. But when the next flood rolls through, the Mississippi might cut through one of these loops, shortening its course and steepening its gradient. By this process, oxbow lakes can form when a meander is totally cut off. The river could change course overnight, or it might take many years to change. Time enough for a town in, say, Tennessee to wake up one morning and find itself in what suddenly become Arkansas. A river's drainage basin is defined by its wettest tributary, the longest stretch of a river from headwaters to mouth, the total area from which a river's water flows. A drainage basin is the total area from which a river's water flows. At its mouth, the flow or discharge of the Mississippi averages just under 600,000 cubic feet per second, or CFS, by that measure making it the 8th largest river in the world. The river's discharge is hardly constant, though. Floods radically change the river's personality. High flow events on the Mississippi are not brief flash floods, but rather regional floods that build and subside over many days or even weeks. In 1927, high water forced almost 1 million people from their homes, not quite 1% of the United States' total population at the time. During the flood of 1993, 75 communities were underwater as 1 million CFS rushed past St. Louis. Further downstream in 2011, more than 2 million CFS swept past Vicksburg, Mississippi. Discharge is one measure of the river, but there's also the flow velocity or speed of the current. You might think velocity would be controlled primarily by the river's gradient, that is, by how much the bed drops over a given length of channel. But you'd be wrong. Gradient matters, but discharge matters more in determining the Mississippi's flow velocity. The basin's tributaries, for example, plummet thousands of feet as they first leave the high Rockies and the rugged Appalachians. But by the time it passes Mark Twain's home in Hannibal, Missouri, the main stem Mississippi has less than 500 feet left to fall before reaching the Gulf, 1,260 miles downstream. Even though the gradient of the remaining riverbed is low, the river flows faster here than in its upper stretches, and at flood stage, the lower Mississippi can accelerate to 8 or 9 miles an hour. With increasing velocity comes turbulence and a dramatic increase in the river's ability to erode its banks and bed. There is also a greater ability to carry sediment downstream, either suspended in the rushing water or rolling and bouncing along the bottom as bedload. In 1927, floodwaters inundated 27,000 square miles along both sides of the river from southeast Missouri all the way to the Gulf, submerging some communities and fields under 30 feet of water. Of course, floods like this are catastrophic, but they're part of the river's natural behavior. Before the advent of artificial levees, floods would build natural levees as sand grains settle out just beyond the river's normal banks. Beyond these levees, high water would often cover the Mississippi's floodplain that stretched up to 70 miles beyond the river's edge. This level, fertile floodplain has been plowed into farmland that now helps to feed much of our nation and the world. A greater load of sediment, however, has always been carried on downstream to the river's mouth. As the Mississippi approaches sea level at the Gulf of Mexico, it slows down, breaks into channels called distributaries, and begins to drop its prodigious sediment load, something like 230 million tons a year. The result is a massive delta. The building blocks of the delta are a mix of small and larger particles. Coarser grains tend to drop out early as the river slows. Some fine particles are deposited on the delta, but most remain in suspension and travel well out into the Gulf. For the past 6,000 years, ever since sea level rose and stabilized after the Quaternary Ice Age ended, the Mississippi River has been building up its modern delta, first one lobe, then another, as accumulating sediments repeatedly divert the river's flow. So far, the river has created 7 of these deltaic lobes. Someday it will jump from its current channel and flow down the Atchafalaya River in a shorter, steeper route to create yet another lobe. If the river succeeds in switching to a different channel, as indeed it someday must, cities like Baton Rouge and New Orleans will no longer have river access. The U.S. Army Corps of Engineers is trying to prevent, or at least delay, this geologically inevitable event because of the staggering negative economic impact. People have moved up and down the Mississippi for hundreds, if not thousands of years. The river is famous for its iconic paddle wheel steamers, but those were displaced with the advent of diesel engines. Now towboats push 6-acre barges laden with fertilizer, grain, and coal, commerce that sustains the nation's midsection. The Mississippi is a working river. As America's most important waterway, it's been heavily manipulated. Above St. Louis, 42 locks and dams aid navigation, affect the flow, and trap the river sediment. Artificial levees have reduced the seasonally wetted floodplain area by 90%. Millions of people living along the Mississippi rely on treatment plants to make the water drinkable, even though it's been used and reused many times upstream. Fertilizers are flushed from farmers' fields and enter the river. These chemicals are carried downstream to the Gulf of Mexico, where they promote the growth of algae, which, when it dies, depletes oxygen. In this way, a 7,000 square mile hypoxic dead zone has been created off the coast of Louisiana and other Gulf states. With so much industry along the river and so much agriculture spread across its floodplain, pollution has to be managed and minimized. We ask a lot of this great river, and we've profoundly altered it in modern times, but it continues to shape the heart of this country. What did you learn? The Mississippi River's flow velocity is primarily controlled by gradient, discharge, channel roughness. Discharge controls the Mississippi River's flow velocity, or speed. If you had to choose, which one of these stretches would you say is lower in the Colorado River basin, and why? Rapids on the Colorado River show that it's quickly losing elevation as it tumbles through Cataract Canyon in eastern Utah. By contrast, the river has a much lower gradient as it flows peacefully through the Imperial Wildlife Refuge on the western border of Arizona. Lower gradient can suggest that a river's mouth is close by.
So one of the ways we can look at the way that a stream flows is by looking at the longitudinal profile, which is sort of a cross-sectional view of a stream along its length. So it's from the head to the mouth, and you're looking at basically how it heads downstream. So the profile is a smooth curve where the gradient decreases from the head to the mouth. And you'll see factors that will increase as you head downstream. The velocity and the discharge will both go up as you head downstream. So here we have a stream. There's the head, it's steeper. You have a longitudinal profile. This is the longitudinal profile. It's more gradual as it heads towards the mouth. There's a sudden drop off here. This is like a waterfall or something. And then it's a more gentle gradient at the bottom close to the mouth. And we'll generally see as we look at this sort of thing, as we head downstream, discharge goes up. The speed goes up, the roughness goes down. So additionally, the channel size will increase downstream, and things that will decrease are the gradient or slope and the channel roughness. So as you go from the head to the mouth, the slope will decrease, the roughness will decrease, it'll get smoother and shallower. The velocity will increase, the size of the channel will increase, and the discharge will increase. And the channel size and velocity increasing is mostly being driven by the discharge. So this is a video about the changes in the river, in a stream, from its head to the mouth.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. And after watching this video, you should be able to describe the changes that take place along the course of a stream from its headwaters to its mouth. Now, this is a look at a stream that's fairly close to its headwaters, and you can tell that it's pretty close to its headwaters because you can see mountains in the background and lots of really big particles of sediment and rushing water that has a very steep gradient. So all of these are sort of symptoms of what we would expect to see near the very top end of a stream. So the headwaters, like we were just looking at, are over here on the left of this picture, and you can see little tributaries merging in this region of headwaters, raging mountain streams like the one we just looked at that merge into larger trunk streams. The photo that we just looked at is sort of the zone of sediment production or erosion, where those mountains are actively being eroded, dumping sediment into the stream. There'll be another zone further downstream, which is the zone of transportation. That's where you have a proper trunk stream. That trunk stream may show meandering, and then eventually it gets down to where it finally ends up in the sea or whatever its final destination is. And that, of course, is where the sediment gets dumped. It's the zone of deposition, and we refer to that as the mouth of the stream. Here's an example from real life. This is looking west at the Sierra Nevada of California with the Great Central Valley in the foreground and the Owens Valley way off there in the distance here in the background. And you can see that there are several different little tributaries here that come together and they merge and then they flow down as the Kings River through the Great Central Valley of California. Now, if you plot the elevation of the Kings River from its head to its mouth, you get the graph shown up here at the top. And you can see that the gradient is much steeper up near the headwaters, and then it basically flattens out a bit as it comes into the foothills region here of the Sierra Nevada, and then it gets very flat indeed, with one exception, all the way to its mouth. So there's a little nick point there along the stream's gradient. But other than that, it's a pretty smooth drop. So if we wanted to summarize the trends that we see from the headwaters to the mouth, we can plot that on this graph. So essentially what we're going to show here is increasing in different trends on the vertical axis, and then distance from the headwaters to the mouth on the horizontal axis. The first thing we want to take a look at is the channel slope or gradient, and that was what we just examined with the Sierra Nevada Great Central Valley example. Basically, it's steeper uphill near the headwaters and it gets more gentle towards the mouth. A second factor is channel roughness. The channels are much rougher up towards the headwaters, and they tend to get smoothed out and abraded to smooth channels with low levels of roughness. Another variable we might consider is how fast the stream is flowing, its flow velocity. Near the headwaters, it's actually relatively low flow velocity, and near the mouth, it gets to be higher. A fourth variable we might consider is how big the channel is, how wide it is, and how deep it is. What's its cross-sectional area? And obviously, up near the headwaters, you just have tiny little rills, which have almost no channel size at all. And when you get down towards the mouth, that's where the stream is most well developed, and so you have a large channel size. What about the total volume of water that be passing through the channel? What would your guess be as to discharge? Is discharge going to be higher near the headwaters or higher near the mouth of the river? Well, hopefully you said that it'd be higher near the mouth of the river, and indeed that's true, because the further down you go on a river, it's getting more and more water from its tributaries. It increases towards the mouth. Nicely done. Thanks very much for your attention. This has been another Smart Figure.
So let's talk about some of the things that running water can do. So at some level, there's three things that water does with sediment. It erodes it, picks it up, it transports it carries it along, and then eventually it deposits it. Puts it back down. Now, erosion is that process by which various bits of sediment are picked up and carried into the stream and carried along. Transportation is how that one material is moved. So transported material is called the stream's load. We can divide the stream's load into 3 parts. One portion of this is the dissolved load. This is the portion of the stream. This is the minerals that have dissolved in the water and are just carried dissolved in the water of the stream. Minerals dissolved in the stream. This is the hardest part to remove. It's always going to stay there until the water evaporates, basically. Then we have the suspended load. The suspended load is carried, it's particles suspended in the stream. You know, when you see a murky river, it's those particles. The various particles and objects carried along in the body of the stream, but often if the water has a chance to sit still, this is stuff that'll settle out to the bottom if the water sits still. So what is carried in the suspended load in many ways depends on how fast the water is moving. So the faster the water moves, the more stuff it can carry, the bigger stuff it can carry. And when it slows down, the heavier material will start to settle out. And lastly is the bed load. These are larger particles that are sort of bouncing along on the bottom. They're not light enough to be picked up and carried with the flow of water suspended, but they are light enough to be pushed along by the flow of water and bounce along on the bottom of the bed. So the dissolved load is invisible because it's actually dissolved in the water. The suspended load is things like silt and clay. It's what makes rivers like the Mississippi all murky. And then the bed load is things that are either they're salutating, bouncing along the bottom, they're sliding along the bottom, or they're rolling along the bottom. And this is bigger objects like sand, gravel, boulders. So this is a short video about that sediment transport by streams and the different loads.
Stream sediment movement. Rock transported by the flowing water of a stream is known as the stream load. The stream load moves in several different ways. Some compounds, such as salts, may be dissolved in the flowing water. Very fine particles of clay and silt are carried in suspension without touching the stream bed. Larger particles, such as sand, may jump or bounce along the bottom in a process called saltation. The largest particles, such as gravel and cobbles, slide or roll along the bottom in a process known as traction. Material moving in solution is known as the dissolved load of the stream, while sediment moving in suspension constitutes the suspended load. The larger material moving by saltation or traction makes up the bed load of a stream.
So that load will vary from dissolved material to fine particles to large rocks. And the stream load at any given location or time will depend on a few factors. The stream's gradient, the stream's volume, the velocity of the current, which is a big factor, and the material that the channel is made of. It's usually divided into those 3 components, depending on how that material is carried by the stream: the dissolved load, the suspended load, and the bed load. If you take like a jar and dip it into a stream, you're going to not pick up the bed load because it's on the bottom of the stream. The suspended, if you let the jar sit still, the suspended load will settle out on the bottom of your jar, and the dissolved load will remain in the water at the top of your jar. So the dissolved load consists of minerals and elements carried by the stream in solution. Up to 20% of the stream's load could be this dissolved portion. The suspended load consists of fine to medium grade discrete particles suspended in the flowing water. It will change dramatically depending on the velocity of the flowing water. Faster the water flows, the bigger the particles it can carry. And the bed load is larger grains that roll or bounce along the bottom of the channel. And here is a video showing an actual bed load in Alaska. So this is some actual streams in Alaska. Moving along the heat, see salutation, and rolling and such. It's the process of material moving along the bed. Gravel carried along by the object. See how larger material doesn't move as much. Now, the load is related to a couple of factors. The street's competence, which is the maximum particle size it can carry, and its capacity, the maximum load it can have, which is related to its discharge. How much material you can carry is related to how much water you're moving. Now, deposition of material is generally caused by a decrease in velocity. Because when velocity is reduced, the competence, the size of the particles that can be carried, is also reduced. And so when a stream slows down, sediment starts to fall out. So sediment begins to drop out. And the sediments that drop out of a stream, the sediments from streams, are known as alluvium. And these deposits are well sorted because the biggest particles drop out first as the water slows down. So you tend to get groups of particles that are all the same size because the largest material falls out first, then smaller material, and so on. So the faster the stream flow velocity, there's this line, the settling velocity. If you're above the settling velocity, you'll have transportation. If you're below the settling velocity, you'll have deposition. So for particles, and these are different sizes of particles. So the faster the stream velocity, in centimeters per second here, the larger the size of particle it can transport. So very light particles like clay and silt are pretty much always going to get transported. While heavier particles like sand or coarse material, you need to have faster flowing streams to actually carry them, and fast enough. And big enough, it's hard to carry. So the channels of a stream there's several types. Near the headwaters, we have what are called bedrock channels. These are cut into strata. This is where a stream flowing from its headwaters is carving its way into the bedrock. In that area where it's transporting material and it's much more level and it's not digging down much further, you get alluvial channels, which are made primarily of loosely consolidated sediment. This is what you see in floodplains. And these can form meandering streams which move in these sweeping bends. Because if you have any sort of bend, you get more erosion on the outer edge and more deposition on the inner edge, which makes the bends bigger. And so your stream will steadily meander side to side until it, say, hits the edge of your floodplain and wears away there, or until there's some sort of flood that cuts off it, and so on. And you can also have braided streams where you have lots of complex networks of channels that flow in and out of each other. You don't have one big channel, you have lots of little channels flowing in and out of each other. So here's an example of a braided stream, where instead of one big stream cutting across, you have lots of little streams separating and reconnecting all over the place. So in the upstream portion of a stream, the flowing water will erode out a V-shaped stream valley as it cuts through the bedrock. And then as it eventually reaches close to the level of the standing body of water that it's going to flow into, it's not going to have much urge to go down anymore. And so it can't really erode any further down. And so it'll start eroding side to side, and you get more of a wide floodplain with sediment. So most streams empty into the ocean, therefore sea level is the lowest level to which a stream can erode. And streams that empty into a lake have the lake level as their lowest level of possible erosion. And the base level is the lower limit below which a given stream can't erode, and that's usually sea level. So as streams shape valleys, the base level is the lowest point that a stream can erode to. There's two general types. The ultimate base level is going to be sea level. Streams can't get below sea level, erode below sea level, because they're flowing into the sea. There's nowhere for them, no more down for them to go. But you can have temporary or local base levels, like if it's flowing into a lake that's at a higher altitude. If you build a dam, that will raise the base level of the stream above that dam, things like that. And changing the base level causes readjustment of the stream, either deposition, the dumping out of material, or erosion, the wearing away of material. So if you effectively raise the base level, material is going to deposit because the stream is going to slow down, stuff's going to fall out. But if you effectively lower the base level, which is something that happened with the Colorado Plateau, because the whole plateau got pushed upwards, that'll cause erosion. And then you can have meandering streams, which normally wouldn't form deep V-shaped valleys, cutting these V-shaped valleys straight down, and you get some really impressive things along the Colorado. So one of the things you can do, you build a dam that's going to raise the base level, and you're going to get a new stream profile formed by the deposition of sediment, because sediment is going to deposit more towards that base level. So that would be raising the base level. You do something that lowered the base level, like you got rid of a dam, you would get more erosion. So in the head areas, when you're well above the base level, you get valley deepening. This cuts a V-shaped valley that cuts downwards towards the base level. If you had meanders that got uplifted, like in the Colorado Plateau, you can get incised meanders, where you had these curves, they get carved into the bedrock. And features you often see in areas of valley deepening are things like rapids and waterfalls. As the stream in that area, the gradient is quite steep. So here, for example, is the Yellowstone River. You see the waterfall here, the rapids here, and you can see how this is a deep V-shaped valley cut as the river wears its way down at the bottom of the surface. Now, when the stream is near the base level, it stops eroding as much at the bottom and starts eroding more towards the sides, and it widens the valley. Downward erosion becomes less dominant. The stream energy gets more directed from side to side. And as the stream shifts from side to side via meanders and other factors, you can produce a broad, flat valley floor made of deposited material, alluvium. This is a floodplain. These are great for agriculture because they just have really nice soil, but they do flood all the time. So in the downstream portion of the stream, the level of flowing water approaches the stream's base level. And in this region, the downward erosion slows and most of the stream's energy gets expended laterally to the sides. And during flooding, the stream will overflow its banks and deposit sediments over a wide area. And so this will develop a widened flat valley floor called the floodplain. So near the headwater, over time, you start with the narrow V-shaped valleys. Then eventually you get near the base level and you start eroding side to side, widening that valley out, making it a broad, flat bottom valley. And you have a large area that's full of deposited material. That's this well-developed floodplain, which often gets used for agriculture. This is sort of the development of the floodplain over time. And here is a short video.
In this video, we are visiting Missouri Headwater State Park, where 3 rivers converge to create the Missouri River. To the left, we see the Missouri River. As we pan, we can see a wide sweeping meander of the Gallatin River in its floodplain. A floodplain is the flat area around a river extending from its channel to the edge of the wide valley. Let's look a little more closely at the water flowing in the channel. What can you observe about the velocity of the water flowing in the inside versus the outside of the bend in the river? Around the inside, it flows more slowly. Around the outside, more quickly, because it has farther to travel. Looking at the 2 sides of the stream channel, we see certain features. What is this pile of sediment around the inside of the bend? That is a point bar. Do you know how a point bar forms? As the water flows around the inside of the bend, the velocity decreases, and so the competence, or the ability of water to transport sediment, decreases, and so sediment is deposited. With this in mind, can you describe the process on the other side of the stream? The increase in velocity of water flowing around the outside of the bend increases the competence and leads to erosion along the outside bank of the channel. This continued erosion has led to the creation of the bluff that you see on the right. The point bar is always on the inside of the bend and the cut bank on the outside. See here where the river bends to the right? The point bar is on the right. And further downstream, as the river bends to the left, the point bar is on the other side. Here we are looking at a bend in the Missouri River. On the other side, you can see the point bar. Let's look closely at the cut bank. You can see blocks of the upper part of the bank that have fallen down a steep slope into the stream. This material will be flushed downstream, and more of the bank will continue to collapse into the water, thus continuing erosion at the cut bank. So, as a small bend in a river's path causes erosion at the cut bank and deposition at the point bar, This erosion and deposition will cause the curve of the bend to become more exaggerated. Then, as the bend gets bigger, the erosion and deposition are enhanced by the differences in water velocity. Over time, the channel will develop a more sweeping bend, and it will migrate laterally. As we look at a cut bank beneath our feet and a point bar across the stream, let's sketch this migration and cross-section. Over time, erosion occurs at the cut bank and deposition occurs at the point bar, causing the channel to migrate. As the cut bank continues to erode to the left and the point bar continues to grow from the right, the channel moves to the left. In this satellite image of a meander in the Ohio River near Evansville, Indiana, you can see what are called scroll bars that were left behind during the migration of this channel. The bend in the channel has migrated to the south, and the bend has become more and more exaggerated. Looking at this time-lapse of satellite images of the Paraná River in South America, you can see that over 28 years the river channel has moved. We can trace the location of the river in 1984 and see how far it has moved by 2012. You can also see the scroll bars that have been left behind. Now we return to the Missouri headwaters to take a wider look around the area. The flat area to the right of the channel is the floodplain. At this meander of the Gallatin River, the channel is at the edge of its wide valley. You can see the flat area to the left of the channel is uniformly higher than the current floodplain. What will happen in this area in the future? A, the channel will migrate to the right, making the valley wider. B, the channel will migrate to the left, making the valley wider. Or C, there will be no change in the location of the channel. The correct answer is B. The channel will continue to erode on the left side at the cut bank, which will make the lower elevation floodplain even wider.
So that as these floodplains, well, they flood. So new sediments they receive periodically within this floodplain make these areas some of the most fertile agricultural land in the world. And these rich soils also leads most floodplains to become heavily populated, which then leads to lots of people getting flooded when they flood. But despite their usually quiet appearance, floodplains are still prone to periodic flooding, causing significant damage to crops and structures. And a lot of the techniques we use to try and eke out more land and control rivers make those floods worse. So it's kind of complicated. And particularly in the downstream portions, the stream will twist and turn, leading to loop-like bends called meanders. Essentially, the stream will always take the path of least resistance, and at the outside of each meander loop, the current's slightly faster, that causes erosion. On the inside, it's slightly slower, causing deposition. And when an entire loop gets cut off, you get what's called an oxbow leg. So if you get a bigger and bigger loop, and then you have something happens to cut on through, and that loop sort of gets abandoned, you have this oxbow leg remaining. So this is an animation showing how an oxbow leg forms. So you have, because the meanders increase in size, you have a eventually dry out and just leave depression. Yes.
Oh, I was gonna say, why wouldn't it have done that near the bottom instead of the top?
You mean here? Chance. In many ways, it could happen at the other place as well. It's just where things get close enough to connect. So probably it was just a little closer at top, or that's how they animated it. But here you can see that, you know, there's one here where this stream meander got cut off. So here's an Oxbow Lake. There's another one over here where stuff sort of went this way instead. Now, you can have some interesting effects when there's a change in baseline. So you can have like a whole area rise up, or you can have a sea level change, things like that. That can cause a change in baseline, which can create things like incised meanders and stream terraces. Incised meanders happen where you have a river meandering on a floodplain, and then that floodplain gets uplifted, pushed up by some force, and then that river will just start carving straight down, because now it's well above its base level. So this
Hello,
is a video
this is
about
Callan
how
Bentley.
those form.
Welcome back for another Smart Figure.
And the Colorado River
After
has
watching
some
this
very
video,
impressive
you should be
ones.
able to describe what processes would have had to take place to produce an incised meander. In a previous Smart Figure video, we talked about meandering, and we said that as river currents make their way around curves in the stream, the strongest part of the current ends up getting deflected towards the edge. This generates erosion at the cut bank and deposition at the point bar. However, sometimes we see meandering streams that are locked at the bottom of deep canyon. The meander is no longer moving side to side in the same way as in the image that we just looked at. Instead, it seems locked in place by being incised into bedrock. So we call these incised meanders. Now we know that streams develop frequently in this sort of a fashion, where you start off with a narrow V-shaped stream. So up here in the upper right, you can see a V-shaped profile as that stream is cutting into that landscape. As time goes by and the river begins to meander, it moves side to side and erodes the sides of the valley. So it ends up defining a well-developed river valley. And then that river valley can actually get wider over time. So here's the overall river valley. Of course, the river is just a very small part of that. But as it meanders, it tends to focus erosion when those meander edges touch the edge of the river valley. At the bottom, we've got these very nicely well-developed meanders, and you can see even some oxbow lakes there. How can we get from that situation to the incised meander that we saw in the previous picture? Well, I hope you would think it probably has something to do with base level. And so that is indeed the case. In order to get an incised meander, you have to start off with a meandering stream, like this example here. But then that has to experience a change in base level so that it no longer is moving side to side. Its energy goes into cutting downward into the landscape beneath it. In other words, it incises. And once that happens, you can end up getting the most spectacular landscapes with these big looping meanders that are at the bottom of big deep canyons. Thanks very much for your attention. This has been another Smart Figure.
So those are some features produced by erosion. There are also features produced by deposition. So deltas occur when a sediment-laden stream enters a still body of water. It suddenly slows down, it basically loses all of its competence and dumps out its sediment. Additionally, in streams, as they flood, they tend to deposit their large particles of sediment nearer to the edge of the stream, and then smaller particles further down, and this builds up natural levees. So you get buildup of sediment parallel to stream channels on both banks. They get a little bigger each flood because as a river floods, the water that floods over is moving more slowly. It dumps out material along the banks and builds up the banks of these levees. And the area behind these natural levees can contain things like back swamps, which are these swampy areas behind the natural levees, or what are called Yazoo tributaries. Yazoo tributaries are small tributaries that run sort of parallel through the trunk stream. And if you go from a very steep gradient to suddenly a very flat area, you get what's called an alluvial fan. The sudden drop in velocity due to a mountain stream shifting to a less confined channel at the base of the mountain, the water can spread out and slow down, and it just dumps sediment out in a big fan-shaped structure. So as streams deposit material, they erode and transport enormous quantities of material, and most of these sediments eventually end up in the ocean, where the stream ends. And the Mississippi River, for example, carries 500 million tons of sediment into the Gulf of Mexico each year. And most of these sediments will accumulate at the mouth of the stream as the stream velocity significantly diminishes, and these form the stream's delta. And it's called a delta because it's triangular, like the letter delta, the Greek letter delta. So here is an illustration illustrating the process by which a simple delta forms. First, you get a stream sort of extending out into the, depositing sediment as it flows outwards. You get a buildup of sediment alongside, building outwards, going further and further out. Eventually, you get a moment where it'll break through somewhere and extend in a new direction, depositing sediment as it moves out. And that old one will just sort of backfill, and then it'll do it again and again and again, and it'll build up this sort of wide delta structure. So these are called distributaries. And you get, say, beds of sediment deposited on top, other beds of sediment. You get coarse particles that drop soon after entering the water body, and then as the delta grows, these beds cover the bottom set beds, which are fine silt and clay particles that settle beyond the mouth of the river. And then you get top set beds that are deposited on top of the foreset beds during floods. You can also get the formation of natural levees. Natural levees form as a stream floods. When a stream floods, the coarse sediments will fall out as the water slows down at the edge, as it floods out over the edge of the stream, and the fine sediments will deposit further down. And after the flood, the stream will settle back down, but there'll be this pile of sediment on either side. And that process repeats with each flood, building up these natural levees. After numerous floods, you can build up these natural levees that can build up the banks of the stream higher and higher. So with the process of flooding, you get the development of natural levees.
Flooding and natural levee development. Many of the features of a stream floodplain are the result of periodic flooding. Water from the rising stream spills out over the banks and inundates the floodplain with silt-laden water. After the floodwaters recede, notice that new deposits of alluvium have been left on the floodplain. You now see a cross-section of the stream channel. Notice the sediment-rich water that spills out of the stream channel during the flood. As the floodwaters recede, alluvium is deposited along the banks of the stream, building up natural levees. Natural levees are often the highest point on a stream floodplain. Notice the small stream on the floodplain to the right of the main stream. This is known as a Yazoo stream. A Yazoo stream is a tributary that runs parallel to the main stream on a floodplain because it is blocked from joining the main stream by the natural levees formed by the larger stream.
Okay. And I think So let me just check where we are in the chapter. Oh, no, we can go a little. So let's talk about floods. Floods are the most common geologic hazard. They happen all the time. And floods can be caused by a number of factors. The weather, it can rain a lot, and thus things flood. And you can also have human interference with stream systems, can both make floods more likely, you can also cause floods and exacerbate floods. So messing around with stream systems can cause floods and make things more adequate. So some of the ways we try and control floods, we can do engineering efforts. We can build artificial levees and flood control dams to control the flow of water through rivers, or we can channelize rivers where you constrain them to a strict channel. Now, these can only go so far in many ways. And in a lot of ways, a more modern approach has been a more non-structural approach through sound management of floodplain and the reestablishment of things like wetlands and such that can help absorb the water of floods and slow down the process and mitigate this and help prevent this collapse of levees and issues like that. And with a, more an approach for mitigation and control that's a little closer to what naturally occurs. So here's an example of a really dramatic flood. This is the Burns Point, New Madrid floodway, where this is a large flooded area. Floods are going to happen. Lots of people live in floodplains. Yeah, so let's stop there and we'll move on to groundwater after this. And if you gave me your homework number 3 on paper, I have them up here graded.